Alright, so here's question 11 from the sample exam 2 that we looked at on April 3rd, Thursday. That was yesterday. And I'm going to summarize the information that you're given here. So you've got x1 is negatively related to y. So that means if I increase or decrease x1, that would imply a decrease or increase with y. And that's beta 1 is less than 0. And x2 is negatively related to y, so that means the same thing. If I increase or decrease x2, that implies I decrease or increase y, and that's beta 2 is less than 0. Finally, if I increase or decrease x1, there's a correlation with x2 in the opposite direction. I'm going to increase or decrease or increase x2. So R12 is less than 0. Okay. Now, so look at that carefully, and now we're going to go in and try to illustrate the true model next. So I'm going to put y on the vertical axis and x1 here, and we're trying to illustrate the effects of x1 on y, and in the true model we look at those effects when the x2 is actually held constant. And it should be what we're measuring, beta 1 is measuring that effect. And so conceptually what that looks like, that's point 1, here's x1 initially, y1, and when I lower x2 to x12, that moves me along the relationship where x2 is held constant, and I go up to y2, right? So I've got a decrease in x1 leading to an increase in y. Beta 1 is less than 0. That's what we're out to demonstrate. And keep in mind that the change in x2 here is equal to 0. So this movement from 1 to 2 measures the change in y brought about by a change in x1 holding x2 constant, and that is equal to beta 1, which is less than 0. Right. So now the idea is, well, when I decrease x1, that happens with an increase in x2. And an increase in x2 leads to a decrease in y. This is because beta 2 is less than 0. So what we're going to do is show what effect that has on this relationship. So this is x1 still, this is y, and what I'm going to do now is x2 is not held constant, it's at a given level initially, and I'm going to put in my points 1 and 2 here. These are the same points that we just drew. So the idea is, remember that, well, when x1 is falling, x2 is rising, and x2 is inversely related to y, so let's start from point 2. Suppose I decompose this. In addition to the effects of x1 on y, the x2 going up when x1 goes down tends to push y down. And we'll use this. This is actually x12 here. And there's 3 possible scenarios. I could have y come down that far, and this over here is y1. I could have it such that I get right back to where I started from with respect to y, or I could get pushed all the way down here. And so the idea is x2 is changing. In this diagram, what that looks like is I'm shifting the relationship in to reflect that x2 2 is greater than x2, 1. Okay? And so I wind up at this point, and I'm going to call this y2 star. And this was y2, the original. So the idea is I'm actually coming up with a net result that when what this point here is telling me is that when I decreased x1, that's telling me that y actually decreased relative to its initial value at point 1. And so instead of, we know the true population coefficient is less than 0, that is beta 1 looking at movement from 1 to 2, what I'm actually picking up is not this, but I'm picking up beta 1 star greater than 0, and that's this line. And that shows, if you think about what we got here, is x1 decreased and y decreased as well. So it's a positive relationship. And that's how you illustrate the bias. So in this instance, we'd say that beta 1 star is a biased estimate of beta 1, and the bias is actually in the upward direction, because beta 1 star is positive, and that's pushing you up from its true value, which is actually less than 0. I hope that helps.
Made with Doodlecast Pro.